Check out the video first on performing and setting up a titration that I posted to the classroom page, as it does a very good job of explaining and showing you what you'll do in a titration. Once you've had a look at that, then continue on with this mini lesson. In a titration analysis, we have titrant, which is the substance that is in this burette, which allows us to deliver a very precise amount of liquid at a different or variable flow rate. So we can use a stopper, which is located down here, to turn and have the solution enter in a full stream, or we can have the solution enter in a drop-by-drop method. The analyte is in the Erlenmeyer flask, and the analyte could be something we are looking for the concentration of. Sometimes we know the concentration of the analyte and we're actually trying to determine the concentration of the titrant. We also will use an indicator in the analyte that will change color as we add more and more titrant. These are the stages. So we start with our analyte or our sample in our Erlenmeyer flask and our titrant in our burette. We slowly add our titrant into our analyte and we see the color change. Eventually we'll add one drop of our titrant and the color change will turn from yellow to green, or maybe from colorless to pink, and the color will not disappear. In this stage, if I stopped adding the titrant for a minute, I closed the stopper and swirled, that green color would disappear. At this point, the green color no longer disappears. It's there to stay. And ideally, one drop of titrant causes that color change to stay permanently. As it said in the procedural video, the goal of a titration is to get a triplicate answer where we have 3 trials that have very similar volumes of titrant delivered. Our first trial here, when we do the math, gives me a volume of 12.5 milliliters. Our second trial gives me a volume of 11.9 milliliters. Our third trial gives me 12.0 milliliters. And my last trial gives me 11.8 milliliters. This will often happen in a titration. The first trial is usually a trial that we use just to get an idea of the approximate volume. So we often overshoot the end point and our color change becomes too dark. So this one, because it is significantly higher than the other 3, we would eliminate that and we have triplicate with these 3 solutions. Now, the volume of the HCl from these 3 solutions is actually taken as the average. So we have to determine that in order to continue with our calculation. VAV of HCl is equal to 11.9 plus 12.0 plus 11.8 divided by 3. And so our VAV in this case is equal to 11.9 milliliters. And that's for HCl. Now I have my volume of HCl. I also have my volume of my barium hydroxide, and I have my concentration of my barium hydroxide. I now have everything I need to calculate the concentration of hydrochloric acid. So we're going to move to the side so we can have a look at the rest of the calculation. We start with our balanced chemical equation. Barium hydroxide solution is reacting with hydrochloric acid to produce barium chloride, aqueous, and water. We need to balance this chemical equation. I missed the subscript there. We need to balance this chemical equation by putting a 2 in front of the water and the hydrochloric acid. Now, our given information, going back to the question, 10 milliliter sample of 0.0125 barium hydroxide. So volume is equal to 10.0 milliliters and concentration is equal to 0.0125 moles per liter. From our titration, we determine the volume of hydrochloric acid to actually be 11.9 milliliters, and we want to determine the concentration of hydrochloric acid. So there's our given and wanted information. Now, just like we did with all other stoichiometric calculations, we start with our measured amount of our given, so 10.0 milliliters of barium hydroxide, and we're going to multiply by something to get rid of liters and replace with moles, our concentration. And so that's 0.0125 moles per 1 liter. Now I have to multiply by the mole ratio to get rid of moles of BaOH2 and replace with moles of HCl. And my mole ratio is 2 moles to 1 mole. Finally, I have to determine the concentration. Now I have moles on top, which is what I want. So I don't need to have anything up here except a 1. I already have moles. Remember, concentration is measured in moles per liter. I have moles on top right here. I have moles on top. So I do not need to do anything to the top of the equation. I just need to replace the bottom of the equation with liters, and I can keep my milliliters, 11.9 milliliters, because I had milliliters at the start. So those milli prefixes will cancel out. As we work our way across this calculation, milliliters of barium hydroxide, liters cancel, then moles cancel, then we keep the moles and we divide by liters, and we get our final answer. The final answer would be 0.0210 moles per liter. And so that tells me my concentration. The concentration of the HCl solution is 0.0210 moles per liter. So in titration calculations, it's still pretty basic stoichiometry. The one thing that changes is we have to use these 3 volumes to calculate the actual average volume of our titrant that is delivered to make the solution change color. There are a few practice questions very similar to the one I just did in the workbook. Good luck with those and the rest of your work for this week.